All right, let's talk about how we go from a round globe to a flat map. This first video is focused on coordinate systems. This is the process that we go through to get from the Earth, which is a three-dimensional irregular shape, aka the globe is pretty bumpy, to a more regular shape that we can use to make a map. From the Earth, we create something called the geoid, which approximates sea level. This is still an irregular shape, as you can see in the image to the left, but it approximates sea level, so it's not kind of showing the really extreme high areas like, say, the Himalayas, or the really, really deep areas, say, the trenches in the Pacific Ocean. From the geoid, we then create the ellipsoid, which approximates the geoid, and it's a regular shape, aka it's mathematically defined. You can also see this, it's no longer bumpy in that image to the left. It's now a regular, kind of almost spherical shape. Next up is the datum. This connects the Earth's surface to the ellipsoid using control points. How well the datum fits to the globe might depend on what you are mapping. For instance, in the United States, we often use the North American datum because it's highly accurate for our region. You can see this in the bottom image here, where the North American datum really fits closely to the Earth's surface on the left-hand side of the image. Compare this to the European datum, which is highly accurate and closely approximates the globe on around Europe. And you can see that with the red dotted line where it matches up pretty well to the Earth's surface on the right-hand side of that image. WGS 84 is a datum that is kind of a compromised datum, useful for the whole globe. That's not shown on any of these images. Although the Earth-centered datum in the top right image on the left-hand side of this slide is kind of like that. You'll use that datum in the projections lab. Datums get us to geographic coordinate systems, which are when we get to put a 3D version of an XY grid onto the ellipsoid. This is our latitude and longitude. Here we've got latitude lines that run around the globe and longitude lines that go from the North Pole to the South Pole. So now you know that the Earth isn't actually a sphere. It's approximated by an ellipsoid. Unlike spheres, which have equal distance between the center of the Earth and the poles and the center of the Earth and the equator, ellipsoids are defined as having two axes, major and minor. On the ellipsoid of the globe, the major axis goes through the globe and connects two sides of the equator, while the minor axis connects the two poles. Can you think of why the Earth has less distance between the poles than the two sides of the equator? I'll give you a hint. It has to do with centrifugal force. This is called flattening, which could be defined by a ratio that shows how flat the ellipsoid is compared to a sphere. Let's talk a little bit more about coordinate systems. You're probably familiar with Cartesian coordinates from math classes in high school, which let you calculate things like distance and slope across a 2D surface. In spherical land, or really ellipsoid land, these coordinates use angles. This is why when you get your latitude and longitude coordinates, it has degrees listed. Let's dig a little bit more on latitude and longitude. Lines of longitude converge at the poles. These are also called meridians. Which meridian have you heard of most often? Well, it's probably the prime meridian. Lines of latitude are parallel to each other. These are called parallels. They don't converge, unlike meridians. The most famous line of latitude? Well, that's your equator. The length of latitude lines decreases closer to the poles. And latitude and longitude are measured in degrees. We can either show that through degrees, minutes, and seconds, or decimal degrees. Finally, let's quickly talk about great circles. These are the shortest distance between 2 points on the Earth's surface. This is why when you fly to Asia from the west coast of the United States, you go almost over the North Pole. This is actually the shortest line. It just doesn't look like that because of the projection, which is what we'll get to in the next video. Let's quickly recap. You need to know the processes by which we go from the irregular globe to the regular ellipsoid. Why is the Earth an ellipsoid and not a spheroid? Know the differences between latitude and longitude, the alternative names for these, and examples of these lines. Finally, know what a great circle is and when it comes into play. I'll see you in the next video.